Okay, so for this lesson where we take a look at the ambiguous case of the sine law, it is not something that's going to be on your tests for this year, but it is something where if you're planning on transitioning to Math 20-1, it is a part of that curriculum, as well as if you're planning on going to 30-2, it's going to be something that's coming up. So don't worry about getting tested on this, but I just want to, for completeness, make sure this was available so anybody who is wondering about it. So, if I have two students, we're asked to determine the measure of angle ACB or angle C in a triangle in which the length of A to B is 6 centimeters, A to C is 4 centimeters, and angle ABC or angle B is 30 degrees. So we're trying to solve for angle C here. Scott drew this, and he wound up with angle C being an acute angle. Brittany drew the same dimensions, where she still had angle B being 30 degrees, A to C being 4 centimeters, and A to B being 6 centimeters, but she drew angle C as an obtuse angle. The unique thing about this is, given the information that we have, they're actually both possible. So, like, if we take it and actually measured this out, then it actually works. Like, the one that Scott drew, he's got the right lengths and he has the right angle for B. The one that Brittany drew has the right lengths and the right angle for B. They just wound up with two different triangles. So, without using a measuring device, estimate to the nearest 10 degrees what the angle is going to be in each case. Well, I mean, for Scott's, it looks like in here, because this is 30 degrees, and this is going to be a big angle, but if I look at C and B, they look like they're about the same size. So let's say that that one is going to be about, I don't know, about 30 degrees, approximately. And for Brittany's, it's definitely over 90 degrees, so it looks like it's like 110 or 120 degrees. So let's say for Brittany, it looks like about 120 degrees. All right. The work for Scott's diagram and Brittany's diagram is identical in the first four steps. So they said that sine C over C is equal to sine B over B, or sine C over 6 is equal to sine 30 over 4. Sine C is going to equal 6 sine 30 over 4, or sine C is going to equal 0.75. When Scott uses the inverse of sine to determine the angle, then when he puts in sine to the negative 1 of 0.75, he gets 49 degrees. When Brittany is using the guess and check on the calculator to determine to the nearest degree the obtuse angle whose sine ratio is about that much, then she's just putting in, well, sine 120, sine 130, sine 140, trying to get closer and closer and closer. Sorry. And she found that the closest angle was 131 degrees. If we're calculating for the last angle in each case, well, for Scott, because we know what angle C is now, we know what angle B is, we're just trying to find angle A. For Scott, the angle A, or angle CAB, is 180 minus 30 minus 49. The last angle is 101 degrees. For Brittany, angle CAB is going to equal 180 minus 30 minus 131, and she got that the last angle is going to be 19 degrees. So, how do we know if information will produce a unique solution or two different solutions? So in this case, the information given created two possibilities where everything worked, but we could still wind up with two different triangles using the exact same pieces of information. So here's how we're going to check this. It says the graph of y is equal to sine of x for 0 to 180 degrees is shown. And we can see that it starts at 0, it's going up to a maximum of 1, where once we get to 1, that would be at 90 degrees. And then after 90, it's going to come down again until I get to 180 degrees. Now, if I look at this, because it's going from 0 up to 1 and then back to 0 for my y values, well, I have 2 points for the 0.75. I have the two possible angles that are an equivalent distance away from 90 degrees. In this case, I can see that Scott's 49 degrees is going to be 41 degrees away from 90. I can see that Brittany's 131 degrees is also going to be 41 degrees away from 90. It's just one is 41 less than 90, one is 41 more than 90. So if I'm using the symmetry of the graph without using the guess and check feature, well, I can say that if I want to figure out what Brittany's was, then I would take Scott's and subtract it from 90, or 90 minus the acute, to figure out what the distance is between them, and I'm going to add that to 90 degrees. The other way that we could simplify this is say that it's going to be 180, because I have the positive 90, minus the acute angle. So if I'm stating an obtuse angle whose sine ratio is the same for the sine ratio of this, well, then I would just take 180 minus 20. An obtuse angle for this would be 160 degrees. 180 minus 80, this is going to give me 100 degrees. 180 minus 13 is going to give me 167 degrees. And 180 minus 38.6 is going to give me 141.4 degrees. So, I can do that for any of these. If I'm going to solve for the acute angle and the obtuse angle, if I have sine x is equal to 1 over 2, then I'm going to take sine to the negative 1 of 1 over 2, and I'm going to get 30 degrees. There's my acute angle. 180 minus 30 is going to be 150, and there's my obtuse angle. Here I would take sine to the negative 1 of 0.788, which is going to give me 52 degrees approximately, and 180 minus 52 is going to give me an obtuse angle of 128. And I can keep going. Sine to the negative 1 of 5 over 13 is going to be 23 degrees. 180 minus 23 is going to be 157. Or sine to the negative 1 of 7 over 25 is going to give me 16 degrees. And 180 minus 16 is going to give me 164 degrees.